everyone. So in this video we're going to be continuing with the robot color sorter project, and the next step now is that given an image of the objects, how can we detect where the actual boxes are, the cubes are, or any object as a matter of fact. So there's an algorithm called object proposals, EdgeBoxes. So we're going to be using that, and we can find it on GitHub. It's done by Piotr Dollar, and it's called Edges. So to download it, we just click on code and download zip file, and it'll download on your local computer as a zipped folder. And if we scroll down here, just to read a bit of the documentation, it says that it requires the download another one of Piotr's work, which is a toolbox. So if you click on this, it'll take us to this website. And here we can find that the recommendation is to download the latest version from GitHub. So if we click that, we'll end up here. And now we have to also download this as a zip file. Both repositories into our main folder that we're working from. So if we open Edges Master and then we open Edges Demo, EdgeBox Demo, this one, this one. If this opens in MATLAB, all right. Now if we run this, first of all, before we run it, actually, we just need to make sure that this is also added to the path of the MATLAB. So we say selected folders and subfolders so that any functions in this file can be detected. And now if you run this file, so given an image, this code will do edge detection, and then it will try, obviously it's got a complicated, algorithm behind it, but ultimately it will sort of understand that an object is made of connected edges. So it will generate object proposals, so suggestions to where an object is in an image. Sometimes it misses a few, obviously. Sometimes it can obtain some false positives as well, or overlapping boxes. But generally, for our application where the cube is quite obvious, on a plain background, it should perform well, so it should do the job. So in order to use this code, this is the EdgeBoxes demo code that came with the package. So we're just going to copy the lines that we need, which are basically the initialization of the model, the initialization of the options, reading the image, but we're going to skip this line. And finally, this line, which does the main job. So first, let's copy the initialization options, and we're going to paste them here in our code. Now, this is obviously just a bit of a dirty implementation, and we'll tidy it up and modularize it once we're sure everything's working. So here, instead of I'm going to give image, because that's our image. And now I'm going to run the code again. And we're going to see how it performs. So we're going to go to the simulation and run it. So now we have this image. Now when you run this MATLAB code, it's going to connect to the simulation, obtain the image, and then also generate the boxes. So they have been generated. Now we can look at the boxes that are suggested over here. So BBS is bounding boxes. We have the X, Y, width, height, and then a score value of how reliable that suggestion was. Obviously, we can see that it's returned around 800 objects, which is obviously not true. But that's because a lot of the boxes are overlapping. But we can notice that the first 3 boxes have the highest score, and I suspect that these are the boxes around these 3 objects that are the most obvious. Yes, let's try to plot them on the figure just to have an idea of how they look like. So first of all, we're going to use the rectangle function to draw a rectangle. We need to specify the position option, and here we need to input x, y, width, height values, which are luckily just provided by the BBS matrix. So if we say BBS, and let's choose row number 1, and then we need the columns from 1 to 4. If we run this, let's click on run section. Now we can see that we have drawn one of the boxes. Obviously we want more than one, so we're going to put this in a loop for rectangle, or let's say for I equals 1 to 100, or 1 to length of BBS. So let's just draw all of them. And so now if we run this, oh, and now this I need to change to I. So now if we run this, we can have a look at all the bounding boxes. So obviously the performance is not optimal. So we're going to have to change some parameters in order to fix it. The first thing is that the maximum number of boxes detected is 10,000. Obviously that's a major overshoot, so we're going to decrease this to, let's say, 20. And this will significantly improve the performance. So now if I click run section, the detection has happened again. And now if I run it again, obviously I need to clear the figure first and generate it again. So now these are my 20 boxes. Still, what I need is I need to make sure that I only have 3, not more than 3. I need exactly 3 boxes. So I still need to tweak some of these options. I wouldn't want to say maximum boxes equal to 3 because I might have more objects. Also, for example, the algorithm might make a mistake and generate 2 boxes on top of 1 cube, and then leave another cube with no bounding box. So I'll keep this option as is, but what I need to change now is the option beta. And how did I know that? Obviously I did some research. So I dug around. I went to the GitHub repository of Edges. I went to the paper that the author has written. So this is the paper, and I read some of the paper, and one sentence that I need to highlight is this one. A box is removed if its intersection over union is more than beta for a box with greater score. So what does that mean? So so going back to MATLAB, which is here, intersection over union is the ratio between the intersection of 2 boxes over the sum of the area of both boxes together. So the more the boxes are overlapping without any excess from one of them outside the other, the more intersection of a union is closer to 1. However, for example, if we have a really small box, let's say this one over here, really small box, and then another box that's significantly bigger and larger. So it, for example, it completely covers the small box, but it also extends really beyond it. Then the intersection over union is going to be a much smaller number because the intersection is little, whereas the total area, the union, is much larger. So for this score controls if any bounding boxes are going to be ignored if there has been another bounding box that's very similar to it, but with a greater score, with a greater detection score. So currently the default score is 0.75. So let's try changing this to a lower number. So by changing to a lower number, then even if the intersection union is smaller, some of these boxes are going to be ignored. So now let's run this section again, delete the image, run the show image again, and then draw the bounding boxes again. So now we can see that the boxes that were more similar to each other have been deleted, but now we're ending up with boxes that are larger. So these boxes have a lower intersection over union, lower than 0.5. And we're only getting those because we've said maximum number of boxes equal to 20. So even though they're not really great object proposals, they're still being shown. And because we said that the minimum score for an object proposal is 0.01. So if we click on BBS now, we can notice that the first 3 detections have a score of 0.4, and then the rest significantly dropped to 0.2 all the way to 0.1. So what we can do now is we can still, bring this number a little bit down, even more down, because we're sure that no 2 cubes are going to be on top of each other. So really, we're not interested in bounding boxes that are overlapping at all. So we're going to generate the image again, run the options again, and plot the boxes again. And now I'm going to increase the minimum score to 0.2, which is going to be more than the range that I'm not interested in, so this and beyond. I'm going to increase the minimum score to 0.2, which I think is a fair estimate, given that 0.2 is quite far from 0.4. So even if we had a cube that isn't really that prominent in terms of its edges, the object proposal of it will likely have a score more than 0.3. So 0.2 is a fair estimate, is a safe estimate, I'd say. So now we can run this again, this, and now this. And now we obtained our 3 object proposals. You can see that we got an error here, and that's because we've said, so the error is in this line, and it says that the index in position 1, which is this one, exceeds array bounds. So now if we look at the array, BBS, it's got 3 rows only, but the value of I is 4. And why is that? It's because length of BBS, the function length automatically, if you give it a matrix, it just returns the length of the highest dimension. So in this case now it's 5. It's no longer the number of rows. Now it's changed to the number of columns, because the number of rows is now less than the number of columns. So instead of using length, we're going to use size BBS 1. So now we're sure that we're taking the length of the first dimension. 1 here stands for dimension 1, which is a number of rows. So now if you run this again, now there was no error. And also we're going to adjust the width of the lines to make it thicker. So we're going to say line width, and we're going to give value of 2. In the next episode, we're going to be taking each subimage and passing it through a color classifier, which we're going to train in order to find out what color each cube is, in order to find out which box to put it in. Thank you for watching, and if you have any comments or questions, please put them below in the comment section. Thank you again.